Yes.
Okay, so I will start again. I think that was a very nice overview. I did not go through many of the things Professor Sainidis was talking about because I thought he would be talking about them. So I skipped them, and I'm very happy that he actually did that. So if you combine what I said in the beginning and what I will say now with what Professor Sainidis said, you will get a complete picture, not only for refrigerant design selection simulation, but also about computer-aided product design and some aspects of it. Okay, so I will restart from here that there is a question mark on the kind of group contribution or property estimation that has been used for refrigerant molecules. There are other applications where it works fine, but for refrigerant molecules, we are not sure. That's why we did some extra work to check them. And as I said earlier, these are the groups that can be joined together to form molecules. And our view is that these groups are a little bit too big to make the small refrigerant molecules. And one would just take those groups together and join them in terms of the free bonds of each of those groups. And then a molecule should not have any free bonds. And with the groups that are available currently, those small molecules with chlorine, fluorine, or mainly fluorine, carbon and hydrogen are not possible to make. And we did some checks. It is our method, and I don't have any problems of saying it, that our method does not work for these kind of small molecules, which you can see from the table. And then I think it's not just us, other people are using our method and also reporting refrigerants. You can see that R134 boiling point is listed as 236. It is not 236, it is around 247. And so all the other compounds, the predicted values of TB, TC, PC are not really very accurate. And global warming, as I also said, that it actually depends on the data. If people have measured and have good confidence about them, then yes, we can fit them very nicely. But I'm not 100% sure of the global warming potential as well as the toxicity measures. There is big difference in the values, but we are not talking about very accurate values in terms of these properties. We are talking about that as long as we are below a threshold, it is all right. But TB, TC, PC, omega, enthalpy, they do affect the actual calculations, and so they need to be more accurate. So what we have found out was that when we compared with the measured experimental data, this result that I'm showing in the table is not valid anymore, unfortunately. So we started checking or creating a new database of molecules. And when we checked the current database, as I said, there are not that many molecules. There are only 300 known refrigerants, and they're not wide enough to for us to use them to develop new models and accurate models. And even for the 300 refrigerants, there are not all properties are not measured for them. So what we did was, as you can see here, with 1 carbon, 2 carbon, 3 carbon, 4 carbon, And then the bonds are listed. One carbon will have 4 bonds. And then we try to fill those 4 bonds with hydrogen, fluorine, chlorine, amine, OH, iodine, to see how many molecules we could generate. So examples, CH4, we fill all the 4 bonds with hydrogen, and then CH3F, CH2F2, like that. We manually did all of this. So we did not use machine learning because we would have to create a program that the machine would understand. That would require more effort than just us doing it manually. So like that, we filled out all the bonds, all the combinations for single carbon, 2 carbon, triple bonds. I'm not showing examples for all of them, but all possible combinations, we looked at them. And we generated the molecules. This gave us a new database. And then the new database, you can see with 1 carbon, 2 carbon, if you can see my cursor, the first column here has 8,000 compounds. And these 8,000 compounds, we are sure it satisfies the chemistry rules, but they don't exist. What we have found is these molecules, around 3,500, they do exist, but properties are not found for them. Out of these, only 364 were found in our current database, which had property values. And another 65 had the same chemical formula in terms of atoms, but had different structure. So this was the number of molecules for which we had data. These molecules exist, but data is, we are trying to collect data for them. They don't exist, these ones. In other databases, not exactly these compounds that we have generated, but small 1 carbon, 2 carbon kind of compounds, we found about 1,300 compounds. So then we created a database. This is just showing the difference between these and these. We created a database taking these, and these, and we had 1,766 compounds, out of which 306 are non-refrigerants. So then using this as the database, we decided to make a new model with the group contribution, but adding new groups also, new groups that can represent C1, C2 kind of molecules. C3, C4 are possible, but C1, C2 kind of molecules, we needed new groups, more like atomic groups, atom and bond groups. So we had this database, and now we have a new set of groups. And then before I go forward, this is something that also Professor Sainidis mentioned, that if somebody is interested in this kind of work, we have these molecules. We need to generate data for them so that we can develop better models. And note also that since we have generated all the possible molecules here in the CMD, we do not need to generate new molecules. All we need to do is just go to the database and extract these molecules. So the generate past part is already done. So the new property models, we did the model for boiling point, critical temperature, critical pressure. The model looks the same as before, except that we have a different set of groups. And now we are able to get much better error. Before we didn't get so much error. We got mostly errors within plus minus 10%, but we needed plus minus 1% and 5%. Now we have improved that, but we need even better than plus minus 5%, because if a boiling point is 210, 10% means 21 degrees plus minus. That is too much. We need to have within 1%, otherwise those simulation and performance is not going to be very accurate. So we still need to improve here to get it to 1%, but at least we have 5%. And it's much better than what was before. So that's a new improvement. But and as I said, if one wants to use these groups and these methods, the generation of the molecule is already done because we have all the molecules. So all we need to do is calculate the properties. But we have the model now. So what we need to do is go back here and calculate all these properties. We would not have possibility to check how accurate they are, but at least we have a model to predict the properties. So that's advanced, and you can see some presentation of the relative errors and also comparison between the experimental and predicted values. This is for boiling point, for critical temperature, and all of those. And also we can find out exactly which molecules have larger than 10% error. Maybe the groups that we had defined, these small groups, were not good for these. So we are looking at how to avoid them and remove them. Or maybe there is a outlier. We need to check those. And you can see that the number of compounds is not 1,000, it's less, because this is compound C1 to C4. So when we did the modeling, we reduced the compounds further to 1,016 because some of the larger compounds worked all right for the groups that we had. So we are talking about two parallel methods now. One, the standard group contribution method, and one specialized group contribution method only for the refrigerant molecules. So now we have the pure compound, but we are also going to look at mixtures because refrigerant as mixtures have been proposed. And the reason for that is if we want to satisfy several properties, it's unlikely that one molecule will satisfy all those properties. If we take mixtures, it has more chance of matching more than one property. So that's why mixture properties is very important. And again, these diagrams are for pure compound, but if you see here, this is one saturation line on the left curve. But if it is a mixture, this will not be one curve, this will be a region, and there will be one side liquid, one side vapor, and in between there will be two phases. In this case, you see a region because the single compound is liquid here, is totally vapor here, and the single compound is partially liquid and partially vapor. So that's why in terms of enthalpy, you see part of the enthalpy is for the liquid, part of the enthalpy is for the vapor. Here is only vapor. So we need the same properties, critical temperature, pressure, eccentric factor, that we want to use in an equation of state, but we also need a mixing rule that this Tc, Pc, and omega is not for the pure compound, is for the mixture. And also the enthalpy is for the mixture. So now if we look at the temperature composition diagram, as I said, here is liquid, that's the bubble point, that's the dew point. in between, we have two compositions. So this is one composition, this is another composition. So if we are doing a constant temperature evaporation, we will have one composition here, we will have another composition here. If we do a constant composition change, then the composition here will remain constant, and this will be the bubble point, this will be the dew point. So it depends on now how the cycle operation will be working. Okay, and this is the case for a non-isotropic mixture. So the question then is, should we look for an isotropic mixture or a non-isotropic mixture? And note that the enthalpies at H1, H4, H2, H4, for example, is a mixed. So we need to know what is the composition of the liquid, what is the composition of the vapor, and how much is liquid, how much is vapor. Before the composition, we did not need to worry in case of a single compound, but we needed to worry about the amount of liquid and vapor. This is saturated, this is no problem. This is saturated, no problem. This is supersaturated, is no problem. But if we are in between, we have to worry about the compositions in case of a mixture. And then the question is it better to have a mixture which is non-isotrope or isotrope? It looks like people are considering isotrope because at the isotrope, the liquid and vapor are the same composition. So we do not have to worry about that when we are doing this here operation, it will be the liquid and vapor will have the same composition. So it will work as if it is a single liquid, single compound. But the problem is that this isotrope is at 86%, and the isotopes like R410, R502 are isotopes, but that isotope composition is around 50%. And at 50%, it's not an isotope. So there seems to be a confusion that yes, the isotope, this is an isotope, but the isotope is formed here, not in here. And if they're using the mixture at this composition, then there are differences in temperature and pressure that needs to be accounted for. And then this will change. So those things is not very clear exactly how it is done. And also this isotope should not move. If it is 3.5, at 3.5, the isotope is here. At high pressure, also the isotope should be around the same point. Otherwise, also there is no advantage. So if one is looking for isotrope refrigerant mixture, look for an isotrope which does not move with pressure and the composition is fixed, and preferably around here, not here. If I look at this and you look at the temperatures, it is 255, less than 255. And around here is close to 250. There's really no advantage in taking this isotope. If the isotope was here, there would have been an advantage. So that kind of isotope looks like does not exist yet. So if we want to do the calculation of the mixtures, as I said, these the black variables are calculated. The red variables are parameters that needs to be given. X is given. So some of these variables are given and some are calculated, but the red are parameters that needs to be given. TC, PC, omega unknown, composition unknown, but we need a Kij, that is a binary interaction parameter for equations of state. Otherwise, isotopes cannot be found. The ideal mixture can be calculated by setting it to 0, but then setting it to 0, one cannot find the isotope. One can take ideal mixing, and for ideal mixtures, setting it to 0, and this one will not change very much. Also, these days, PCSAF can be used, and PCSAF does not need TC/PC omega. It needs 3 other parameters: size, volume, it's called epsilon, lambda, and size parameter, and they can be estimated from vapor pressure data, heat of vaporization data, which would need TC/PC omega, but it's a different set of parameters needed. And it also needs a mixing rule. And then giving the mixture composition and these parameters, it is possible to calculate one of these. If R, T, and P are given, VZ can be combined into one variable, and this can be predicted, and similarly here. And then once they are predicted, then the fugacity coefficients can be calculated, and dew point, bubble point, VLE, all of those can be calculated. Similarly for the density, vapor pressure, heat of vaporization, etc. So an additional complication is added when we want to handle mixtures. So now simulation and sensitivity analysis. Simulation, this is the cycle we want to simulate. We can choose whether it is a single refrigerant or binary, quaternary, ternary, quinary. So up to 5 compound mixture can be handled by the model we have done. We have developed because we calculate the PVT relationship and the related data for whether it is single compound or any mixture like that. So step 1, you define the mixture. Step 2, give the composition and the mass fraction, mole fraction, all of that, and the formula. And then the system will extract all the data needed, all the parameter needed, and then it will give you options to define the condenser. That is, do you want to define the temperature, calculate pressure? Do you want to define the pressure, calculate temperature? These options are possible. Expansion, constant enthalpy, and other options are also possible. So then the user has to select those. And then based on the selection, the program will calculate the temperature, pressure, whatever is needed to calculate the enthalpies and work and the heat duties, and then the COP. And then the results can be exported to an Excel file or saved for future analysis. So, and then it can also do sensitivity analysis in the sense both of parameters as well as operating condition. Parameters meaning that once we will do step 4 and calculate the COP or the work or the duties, if we had plus minus errors, let's say the uncertainty in the boiling point, critical temperature, critical pressure was plus minus 5 to 10%, then how would the COP change? Those kind of sensitivity analysis can be looked at, as well as what happens if I change the room temperature or the ambient temperature or the cooling water temperature, what will happen to the operation. So both can be looked at. And this is what we call sensitivity analysis. And so the objective then is kind of what if analysis. How does the COP change if we change the conditions? So this is expression of how will the, if the boiling point changes or the critical temperature changes or the critical pressure changes, how would things change? Obviously, it looks like the critical pressure is not sensitive at all. The boiling point is very sensitive. The critical temperature is also very sensitive. And similarly, we can see the plot in another way. This also looks like that the boiling point is very sensitive because the boiling point determines the enthalpies, the values of the enthalpies, and enthalpies are temperature dependent, not pressure dependent. So then refrigerant selection. I'm not going through the models of the simulation because in lecture 1, I'd already given you how the enthalpy and the COP are calculated. So refrigerant selection, the objective is to find a single, the objective is to find single compounds or mixtures that match a set of target properties and functions. For single compound, we will do database search and CMD that you have already seen. For mixtures, we will have to first identify a set of compounds which are candidates for the mixture, and then we will have to take different candidates and find out whether the compositions will match the target. And once they do, then we can select them for further analysis. So in order to, and I'm not showing now for the single compound, but this is also included. If we want to find a single refrigerant or a binary, ternary, quaternary, we have to set targets. So targets means what should be the property values. And then when we want to do the simulation, we have to choose the conditions for doing the simulation. What is the condition for the condenser, the evaporator, and the isothermic expansion, and also for the compressor. And then we will find the alternative refrigerants, and you will see how it is done, and then we will do the calculations. So there's 4 steps. So what kind of properties do we match? If it is a binary mixture, we have 2 compositions, but only 1 degree of freedom in the composition in terms of mole fraction, because X2 is 1 minus X1. So, which means that if we take a binary mixture, then with composition, we can fit only 1 property. We can match exactly 1 target property. And since boiling point is the most sensitive property, we say if only 1 property needs to be matched, take boiling point. If we want to have a ternary mixture, we have 2 degrees of freedom, so we can take 2 properties, then boiling point and TC or PC. And if we have a quaternary mixture, then we have 3 properties, boiling point, TC, PC. So remember that this one we call target property set 1, that we have to match these properties because TC, PC, omega. Omega is also not very sensitive, so we can ignore that. That either we take omega or critical pressure, that if we have defined this, then we know what kind of PVT relationship we will get. So that's why we say this set 1 target properties need to be matched with the mixture. And set 2 properties are global warming, ozone depletion, flammability, and all those things. Those are desirable properties, but not absolutely necessary. It would be good if those properties are good. So now I will show you with a case study. Here we are replacing R143A, and we want to find single compound replacements, binary, ternary, quaternary. So first, you can see that if we want to set up the target property mixture for boiling point, for critical temperature, critical pressure, the equation is given. The R143A boiling point is 225, critical temperature 346, critical pressure 37. These are measured data. So we want to match exactly this. If it is binary, we will match the boiling point. If it is ternary, boiling point and TC. If it is quaternary, we will match all three. And so the compositions we will get by matching this. And once we have compositions, we will calculate all the other properties and do the simulation. So if we want to make a binary mixture and match the values of R143, obviously the two compounds, binary compounds in the mixture, one needs to have a boiling point higher than 225 and another needs to be lower than 225. Otherwise, the mixed value will never be 225. So what you see are the values that are given here, which are, first of all, close to 225. Sorry, not close to 225. A binary mixture that has been matched exactly to 225 with R32 and R134A in the composition of this. And in a ternary mixture, we have fitted TBTC in this case and TBPC in this case, and then the fit of boiling point TC or boiling point and PC. And then the quaternary is this. Here, we are not showing you the boiling points of each of these compounds, but if you're interested, you can find them. Actually, the step in order to find the compounds, candidates, will already show you those things. And during the demonstration, they will be showing you. So what you can see is that if we replace this one, because it has high global warming, with a binary mixture, we can reduce the global warming and we can improve the COP, but the work here is increased and the Q here is also increased. If we take a ternary, this is increased and the work actually has decreased and the Q also has decreased. So, but the global warming has not decreased so much. Quaternary, this quaternary is not good because the global warming has increased. So we are not showing you any optimization in here. What we are showing you is we can generate all kinds of candidate binary, ternary, quaternary, and do the simulation, test by simulation to find out which one seems to be best. And in this case, the quaternary seems to be best, but the global warming potential, this one, the binary, is better. And then the second example, case 2, is we have a R410A that actually at 83% it forms an isotrope, at 50% it does not form an isotrope. And we want to replace it with a pure compound or single compound or ternary mixtures or quaternary mixtures. And it turns out that a single compound actually is quite good to replace this binary. And then the next one, we have a ternary target. Originally it is ternary. We have possible single compounds that can give approximately this. We have binary mixtures that can approximately give this, and quaternary. But you can see that this one, which has a good COP, the GWP is not good, but this binary is quite good, is lower than this. But this one seems to be the best, just 32, seems to be quite good. So again, what we can show is that it is possible to replace and find candidates that are worth looking at. More experiments need to be done, but these are compounds that exist. More experiments need to be done at those compositions to see if at certain composition and certain operating conditions, they give the best results. And the last one is example of a 4-compound mixture, quaternary mixture, that is replaced by single binary ternary. And in this case, this is quite a good one with very low global warming potential. So then the results are not shown here, but one can also take each of the best candidates and do sensitivity analysis in terms of if the boiling point was different from -5 to -15, from +5 to +15, how would the, keeping all the other conditions the same, how would the performance change for the case of boiling point, critical temperature, critical pressure. And the observation was same, boiling point is more sensitive than TC, and which is more sensitive than PC. With respect to operating conditions, this can be also quite interesting. What happens if we first do the design at the base case, and the base case is red? What happens if we increase the pressure in the evaporator or decrease the pressure in the evaporator? So decrease the pressure is green, increase the pressure is blue. And if we increase the pressure, then actually we get higher COP. So which means that the expansion that we do, we should not reduce the pressure too much. We should reduce the pressure to a certain value, and compared to the base case, if we reduce it a little bit lower, we will get better value. But that means we do not decrease so much. So this will be the lowest value of the pressure. We should have the value of the pressure a little bit higher. And so in this case, when we reduce the pressure in the expansion, we should not reduce too much. That's the message. And that will give higher COP. And in the condenser, it is the opposite. This green line somehow changed. It should have been from here to here. So in the condenser, it is the opposite. If we increase the condenser pressure, we can get better COP. Sorry, if we increase the pressure, we will get lower COP. So if we decrease the condenser pressure, we will get higher COP. So the green one is better. So of course, if we increase the pressure, we have to do more work. If we do not increase the pressure so much, we will have to do less work. So of course, the green is better than the blue. So this kind of analysis can be done very easily on any candidate. And then I've talked about this already in the first lecture. This is the desired temperature we want to achieve. And we can, by selecting a refrigerant, we can define the PVT relationship that is needed for that temperature. And the selected refrigerant will pass the critical temperature pressure eccentric factor for the single compound or the mixture. And once we have generated the PVT, we can calculate the enthalpy, entropy, and other variables. And then once we have done that, we can check the thermodynamic diagram, and we can also check with respect to fluid design, cycle design, and sustainability. So how does the CAMD work? We can say that we are here at the starting point, that is computer-aided molecular design, the framework for it. We define the problem. So problem definition is which kind of problem we want to solve, that is which kind of product. It is refrigerant, is it single, or is it mixture? What are the target properties? We define them here. We convert this problem definition to mathematical form in terms of constraints, in terms of objective function, things like that. So once we have formulated the mathematical problem, then we need to solve the mathematical problem. That can be solved by generate and test, by optimization that Nixainidis talked about, by different ways. And then we have the result. If we get more than one candidate, we can take those and we can do experiments to find out. If we do not get any candidates, maybe our problem definition was too strict. We need to relax them. If we get too many, maybe we relaxed it too much. We can tighten it. So problem definition is very important with respect to also whether we will get a lot of results or not. So solutions of CMD problems, therefore, are iterative. Problem formulation controls the success. Essential qualities versus undesirable qualities. So which are the target properties we want to match? Which are the target properties we do not want to match? And connectivity with external tools, data, and methods are very important because at every step, we need a lot of different tools and they need to be integrated. And that's why a software is needed to do that. So internally, once the problem is formulated here, how is the problem solved? We have different methods to solve it. So first we define the problem, and when the problem is defined, it also goes to the database to retrieve all the data that it needs, not just data of the compounds, data of the model parameters and all that. And then it formulates the problem mathematically. And then once it is mathematically formulated, it can decide which way it wants to solve. Will it solve as generate and test? Will it solve as optimization? Will it solve simultaneously? That is, design the molecule and design the refrigeration cycle simultaneously. Depending on which method is used and which problem is formulated, the data needs will be different, and these will be shown here. So what you see on the left-hand side are the tools needed. What you see on the right-hand side are the data that is needed from here to here to here. As we go along from the top to the bottom, more and more information is coming into the system. And here are the 4 steps that are needed. Definition of the problem, formulation, mathematical formulation, formulation of the CMD problem, solution of the CMD problem. And CMD is molecular design as well as mixture design. So we can solve it through optimization, through generate and test, through simultaneous design of molecule and process, or decomposed. All options are available. And then a little bit about the overview of ProREFD. This is the software that will be demonstrated in the next lecture. It contains, as I said, special database for refrigerants. We have fine-tuned the method for property prediction for refrigerants, but kept also the other methods. So these 2 options are fine-tuned for refrigerants. Modeling will not be shown today. It will be demonstrated in webinar 6. And then refrigerant selection, refrigerant cycle simulation, this will be shown today. What can be done in future? Increase the database contents. As I said, we have more than 10,000 generated, more than 10,000 molecules. We want to add them, but we don't want to add them with no data there. We want to add them with estimated data and cross-checked if possible. So at this moment, the specific refrigerant database has about 1,700. Then we want to improve the property estimation, both for the pure and mixture. We want to continuously improve it. We want to fill in the gaps in the measured data. There's a lot of gaps. We want to add new features for cycle simulation. As we discussed before, we want to add cascade compressors. We want to add organic Rankine cycles, heat pumps, things like that. We want to find mixed refrigerants that can make a difference. With pure compounds, all the known compounds we have already seen, and there is no surprise there unless we make mixtures. So we are looking at mixtures to try to see if a mixture can give us what we want. But the pure compound, unless we can calculate the properties of the new molecules that we have created, there's no surprise in the pure compound. We also want to add the CAPEX and OPEX, that is for the compressor, for the evaporator, for the condenser, expander. We want to do the sizing and costing. Conclusions and perspectives. A further improvement in solution strategy, simultaneous design of refrigerant and optimization of refrigeration cycle, taking into account safety, environmental, and health concerns. Add features to allow organic Rankine cycle, heat pumps, cascade operations, etc. How to fill out the properties for approximately 10,000 molecules that we have generated. Once we have filled this out, CMD, the molecular generation part of CMD will not be necessary anymore. Perform a detailed sustainability LCA performance profit analysis for most used refrigerants and suggest how they can be improved. Add uncertainty issues to the design problem solution. And then the last is some references that you can look at. Also, Sayani, these references are given. So with that, I will end my presentation and see if there are any questions. Any questions? You can raise your hand if you have, or send question in chat. So are you happy with the refrigerants that are being used? Okay. One person has said, yes, nice presentation, but I want to ask you, are you happy with the refrigerants that are in use, or you want to improve them? Maybe to 217 Francis Tecano, you can allow him to speak, unmute him. From the host, can you unmute participant 217?
Yes, he can unmute by himself now.
Want to say something? You can unmute yourself. Francis Tecano. Okay. Okay, anybody else wants to ask any question? Clarification? All right, then I hope you will ask some questions after the presentation of the software. So this will be done by the Thai office, Nichakon and Siripon. Okay? It's your turn now.
Hello. Okay. Hello. Well,
Share your screen.
sorry. Okay, can you see my screen?